This next topic will be dealing with parametric equations. Up until this point, you most likely have been dealing with functions of a form y equals f of x, but sometimes it may not be feasible to describe a function in that form because it fails the vertical line test. So you may have come across that hopefully in a previous class, maybe pre-calc or somewhere along there. And that is that for a curve to be a valid function, if you could draw a vertical line through it, it should only touch once. But you may have a curve where it touches more than once. And so it can't be described in a y equals f of x form in that case. But it can as a set of parametric equations. What a parametric equation is instead of relating y to x, it's relating x and y to a new parameter, which is often t, and you could think of t as time. It's pretty helpful to think of it as time, and time typically starts at 0, and you'll see why I tend to do that. It's not required, but it's a pretty intuitive place to begin for time. So x is often thought of as some function of t, and y is thought of as another function of t, g of t. So x equals f of t, and y equals g of t. Let's get to actually practicing some of this. So what can you do with parametric equations? Well, in the first example, you may be given a set of equations x equals t squared minus 2t, and y equals t plus 1. And you are given the task of describing the curve given by those parametric equations. So one thing that you could do is you can create a sketch. And our sketch is going to be in Cartesian coordinates. And so I've got my x-axis here, y-axis here. Nothing new or foreign about this. And now I need to figure out, okay, so for the time point when t is 0 and 1 and 2 and 3 and so forth, what are the corresponding x and y values? So when t is 0, x is 0 minus 0 or 0, and y is going to be 0 plus 1 or 1. When t is 1, x is 1 minus 2 or negative 1, and y is going to be 1 plus 1, which is 2. When when t is 2, you've got 2 squared is 4 minus 2 times 2, or 4 minus 4 is 0. And y is going to be 2 plus 1, which is 3. When t is 3, you've got 9 minus 6, which is 3. And 3 plus 1 for y, which is 4. And so this is enough to actually get an idea of what our image looks like. So plotting on the xy coordinate system, when t is 0, we have the point 0, 1, which is about here. When t is 1, we are at negative 1, 2, which is about there. When t is 2, we are at 0, 3, which you could see is there. And when t is 3, we are at 3, 4, which is about there. So notice that our sketch looks like this. And what you'll often see is what is the path that if a particle, let's say, obeyed this system of equations, at t equals 0, it started over here. This was t equals 1. And so in time, it went in this direction and continued in that path. And so it's often common if you see parametric equations graphed that you will see a curve, but you'll also see arrows indicating the behavior on that curve, the path that a particle might follow. And that's how you can tell what that path is, knowing each of your time points. So 0 goes to 1, 1 goes to 2, and so forth. Another way that you could get at the curve in an example like this one here is to actually convert these parametric equations, if possible, into a Cartesian equation, so a y as a function of x. And I'll demonstrate that for this one. So we kind of have an idea that it's a parabola, but let's go ahead and prove it. So I see from this equation that I can view t as y minus 1. And if I substitute that t into the x equation, I've got x equals y minus 1 squared minus 2 times y minus 1. Y minus 1 squared is y squared minus 2y plus 1 minus, we've got 2y plus 2. And continuing to simplify, I've got y squared. I have a minus 2y, so minus 4y plus 3. And I notice that this happens to factor into y minus 3 times y minus 1. It's not really necessary to do that, but it can be helpful if you wanted to find y and x intercepts. And so you can always do that and see that we get the points 0, 1 and 0, 3. So when x is 0, y can be 1 or 3. And when y is 0, you're going to get that x is 3. That happens at a negative time point, which is why it's not plotted on here, but starting at a time point of 0 and going upwards in the positive direction, the green curve is what we'd get. But what I see is that we have x equals this parabolic form, and since it's an x equals y squared, I know it's a horizontal parabola, and our image seems to match up with that. Let's move on to problem 2. It asks, what curve is represented by the parametric equations x equals cosine t and y equals sine t for t between 0 and 2 pi. And so in this one, this is a little bit more challenging to see what that Cartesian equation is, but you can always stick with the fact that let's see, that we know that sine squared of t plus cosine squared of t is a well-known trig identity, and that equals 1. And we know that sine is y, so this is y squared. Cosine is x, so this is x squared equals 1. And x squared plus y squared equals 1 corresponds to a circle with a radius of 1. And so wanting to know what the shape is, in this case, we were able to use a well-known identity, and it happens to have an easy substitution knowing what x and y are, and it's a well-known shape. And so going from the trig identity to x squared plus y squared equals 1, and knowing that that's a circle can be very, very helpful. Figuring out how it behaves, we can do a quick sketch. So at time 0, I see that x is cosine of 0, which is 1, and y is sine of 0, which is 0. So this is 1, 0. So I'm starting here. And I like to actually sketch my two curves. So I'm going to do that on the side. So sine, I know, starts at 0 and goes essentially like that. I know it's not perfect, but we've got the general idea. Here's 0, this is pi, and this is 2 pi. And the cosine curve starts at 1 and is going to drop down here drop like that. And so that is going to span from +1 to -1. All right, so let's look at pi. So at pi, when t equals 3.14159 and so forth, we have that x is cosine of pi is -1, and sine of pi is 0. And so that's going to put us here. Now that isn't very helpful because I don't know if we went from the rightmost point up and around or down and around. So we need something in between. So let's go with pi over 2. So at time of pi over 2, x equals cosine of pi over 2, which is the red function. That's going to be 0. And y is going to be sine of pi over 2, which is 1. And so now I know that we progressed. We progressed in upward fashion like this, which means our arrows would follow like that. And this is a circle, so it would continue around in a better circle with constant radius in this fashion. So it goes in a counterclockwise fashion starting at the point of 1, 0. Moving on to problem 3. We want to find the parametric equations for the circle centered at 2, 3 with radius 4. So we already have an idea of what a circle parametric system might look like. X is probably some sine, y is cosine, or vice versa. And so here we just need to figure out how to put it. For a Cartesian equation, I know that that would look like x minus 2 squared plus y minus 3 squared equals, and with a radius of 4, that's going to be 4 squared, or 16. So this is the Cartesian system. And I might decide to declare that, oh, well, sine squared plus cosine squared is what we had in the past problem. So I'm going to choose that x minus 2 is 4 cosine of t, and y minus 3 is 4 sine of t. The reason I have the 4 coefficient is because I know when I plug in a cosine and a sine, I'm going to have sine squared plus cosine squared. That equals 1. That doesn't equal 4 squared. And so I need the 4 in there, which is why I have a 4 for the coefficient of each of these. And then what's left is to just solve for x and y. So the system of parametric equations is x equals 2 plus 4 cosine t, and y equals 3 plus 4 sine t. And that would be our answer for number 3. With the last one being another curve sketch, we want to sketch the curve with the parametric equations x equals sine t and y equals sine squared. And so this is a pretty quick and easy one to see what it's going to look like in the Cartesian form, with x being sine and y equal being sine squared. Both of these together I could see are going to be y equals x squared. So I could see that it's going to be a parabola. But now I need to figure out the actual direction. And so what do we have? Well, I know that the sine function is going to just fluctuate between plus and minus 1. And that means that y is going to fluctuate between 0 and 1. So since sine of t is going to be bounded by plus and minus 1. This implies that sine squared, or y, is going to be bounded between 0 and 1. And this, our first term, that's x. So x ranges from -1 to 1, and y ranges from 0 to 1. So it's good to be aware of that. So that is going to actually confine our parabola. It is not going to infinity in the y direction. What is it going to look like? Well, let's do a sketch. X, we know, ranges from -1 to 1. Y is going to go from 0 up to 1. So at least I know our thresholds. And I know what the curve looks like. The curve looks like that. So now I need to know, well, where do we start? Well, when time is 0, x is sine of 0, which is 0. Y is sine of 0 squared, which is 0 squared. So we're actually starting right here at the origin. And if you choose a time point higher than that, let's look back at our sine function. So sine of pi over 2 is 1. And so that is x equals 1 and y equals 1 squared, or 1, 1, which means we moved to the right. Up to 1, 1. But then after that, when t is pi, the sine function is 0 again, which means that it came back down. So after it went up, it came back down this way and went left. And so the pattern is it goes up, and then it came back down, and it swayed back to the right, and then back to the left. And it's not actually decreasing like I'm doing it. I'm just trying to make the path stand out. And so in this case, it's not just unidirectional. It's kind of like a pendulum and swaying back and forth. But that is a sketch of our curve. And just some things that you could do with parametric equations. More to continue in the following video.